So this video is just a little sidebar on the fundamental particles. So what are the fundamental particles of nature? First of all, what are the properties of the fundamental particles? Some of the properties. Well, some of them are maybe their mass, Again, I'm bringing this up now because a lot of these homework questions, they bring up these particles, but I figured, we should just get a little overview of these fundamental particles. I'm not going to test you on it or anything, but you should probably know these right here. And so mass is one of the properties. Remember, we're going to put that in probably MeV, KeV. Another one is charge. How is it affected by the electric field, the charge? Another one might be, what's its half-life? Another one might be its spin. When I say its spin, I mean its angular momentum. You notice when you brought angular momentum in classical mechanics, you had something that was spinning, and you said the angular momentum is I omega. And omega you can spin as fast as you want or as slow as you want. But for particles, the spin is a constant. It's like the mass. You can't change the mass of an electron. You can't change the spin of these fundamental particles either. Okay. And I should tell you, the units for spin, they're in kind of a unit. I'm just going to call them units of something called an h-bar. It's just a unit of angular momentum. I think it's units of energy times time right there, but it's a certain amount. Okay, and then what else do we have? We might have, let's just look at these properties now. There might be some more that we come along here. So if we take all particles, and we can break them up into two groups. So all the particles, I'll bring it over here so we can, particles. We can break it up into two groups right there. One of them is going to be called bosons. One of them are called fermions. All particles are one of these two types. What distinguishes these two types right here? It really comes down to the spin of the particle right here. All the particles in this group right here have either 1 h-bar of angular momentum or 2 h-bar or 0. They're integers right here. So they're the spin is either 0 or 1, or it could be 2. They're integers, right? So they say it's integer spin. Over here, all the spins of these are half integers. So they're 1/2 an h-bar. Or it could maybe even be 3 halves or 5 halves, but they're not integers right here. So these are half integers and these are integers. You might say, well, what is it? Does that make a big difference? Yes, it does. Electrons, all particles on the periodic table are these. If electrons were a boson right here, then if you look at something like, lead, which is right there, those electrons were bosons, they would all be in the first shell. Normally, you remember from chemistry, there's 2 electrons in the first shell, 8 in the second, and so on. And that's because they're fermions. But if they were bosons, they'd all be in the first shell, and chemistry would be a lot different, and we wouldn't be here. Okay, well, what are the bosons? Usually they call bosons the force carriers right here. They carry the force. So when you have something like the electric field, the electric force between two charges, Q and Q, they might repel from each other. They're really throwing particles at each other. That's what's making them repel right here. And so all forces are just throwing particles at each other. And so the bosons they mediate the forces. So one of them is the photon, the gamma ray photon. We've already had that in some of our examples right there. The symbol for it, we already said, is that. That's going to be the symbol for a photon of light. The charge is 0. It has no charge right there. The mass is also 0, which we said before. The mass is also 0. And does it have an antiparticle right here? Antiparticle. No, there's no such thing as anti-light. So the antiparticle is itself. It has no antiparticle right here. And then what force is responsible for the photon? Remember, these are all responsible for a force of nature. This is the electric force. So this is due to the electric force. Electric. Okay. Then we have something called the W boson. The symbol for it is, it's a minus. It has a charge of -1. It actually has an antiparticle to it. It would be called a W+. I don't know where I'm going to, maybe I should squeeze that in over here. The antiparticle would be the W+ right here. And this one has a mass of 80,000 MeVs. 80,000 MeV. It's pretty heavy right there. And this is responsible for the weak force. The weak force. The reason why it's so weak is because this has so much mass here. Which means when they say something is weak, they just mean that the two particles have to get very, very close before they feel the force. And they have to get really close because this, what they're throwing back and forth at each other, weighs a lot. This was actually discovered in the 1980s. So what I'm talking about now, we're going all the way up to the present right here. Remember I said before we were going to stop at around 1930, but to look at the particles here, I'm going to go to the present. There's also another one for the electric. It's called the Z boson. They just call it Z. It has no charge, Z0 maybe. Well, it has no charge. I'll put a little 0 there. It has no charge, so the charge is 0. And it has no antiparticle. And, oh, I should say, what is the spin of all these? This spin of this, remember, they have to be either 0, 1, or 2, or 3. This has a spin of 1, this has a spin of 1, this has a spin of 1 right here. So these all have a spin of 1. Now the mass, this has no antiparticle. The mass of this is even a little heavier, which is about 90,000 MeVs. Remember, the electron is only a half an MeV, so you had to build a pretty big particle accelerator before they could discover this. This is also due to the weak force, and they found this in the 1980s too, weak. Right at CERN, they found these two right there. Okay. Again, but now you have something called the gluons. You just use a little g. They don't have any charge. They don't have any antiparticle. They have no mass, 0 mass right here, and they mediate the strong force. Strong force. So they're inside the proton, holding the strong force in. Okay. And then we have one other one, which you've probably heard of, the Higgs. Higgs. They usually just call that H0. That has no charge. And it has no antiparticle. And the spin of this one is actually 2. The spin of this is 2. Remember, they have to be integers. And the mass of this is 125,000 MeV. And this is what gives mass its value. So It gives us our mass. And you notice this wasn't discovered until just 2012. 9 years ago, this was discovered at CERN, right here. 125,000 MeV. When I give this mass, this is only an approximate mass. You can't get the mass exactly. Now, there is one force I haven't brought up, and that is gravity. So we could say graviton, it has a charge of 0. I should say we've never seen the graviton, and it's not part of the standard model right here, but and it has no antiparticle, and it has no mass, and it has, the spin is actually 2 on this one. Actually, when I said the spin on this one, I should have said the spin of this one is 0. The spin of this one is 1, 1, 1, 1, 0, and 2 right here. But they're all integers right here. It has no charge. It has no mass, and this is for gravity. But I don't even want to put this one in there because they've never seen it yet. So, but it should be there. Okay, so these are all the force carriers right there. Now, out of this side right here, this can be broken up into 2 groups also. I'm going to write it out more like this. One group here, one group here. One of them is quarks. One of them are, and the other one are leptons. Right here. Now, how are these two distinguished right here? This one feels the strong force. This one feels those gluons right here. These other ones don't even notice them right here. So they both feel the electric force, so they both see photons, but this one sees the strong force, no strong force. That's why leptons don't hang out in the nucleus of the atom. Okay. So what are the names of the quarks right here? Well, one of them is called the up quark, which we'll just use as U right there. It has an antiparticle, which is U bar. Whenever they put the bar, it means it's the anti-up. It's not down. Anti-up is not down right here. Anti-up is anti-up. The spin of all of these are 1/2 right here. The charge is actually a fractional charge. This is 2/3 of the electron. So it's 2/3 right there. The mass is around 2.2 MeV right there. Remember, the electron is 1/2 an MeV, so it's a little bit 4 times the size of it. And you'll notice if we have an up, we have to have a down, D. And it has an anti right there. And it has a charge of -1/3, E. And its mass is about 4.6 MeV. Now I should say that these quarks, each of them come in 3 colors. They come in green, blue, and red. Each one of these. So there's a red, a green, and a blue, a red, green, and blue, and so on for all the quarks right here. Now, when I say they're red, green, and blue, I don't mean that's the color they are. The reason why they give it these colors is, you notice in electrical stuff, you have pluses and minuses. Plus and minuses attract, and like charges repel. But in the strong force, there are 3 flavors. And so how do you distinguish 3 opposites right here? You don't want to say up, down, and in the middle. Those aren't opposites. But color-wise, these are actually opposites. They're primary colors, the red, green, blue. And when you add these 3 colors together, you get white right here when you add those 3 colors. Okay. There's a reason for that at the end, so I'm just going to say that each one of those come in, they call the color charge right there. Okay. Now, there's going to be another one that looks kind of like, here was my up and my down. They kind of go together right there, up and down. But in the late 60s, early 70s, they found another group that kind of goes together. One of them they called C for charm. They called that C right there. It has an anti one, which would be C bar. It would have the same charge as this, 2/3 right here. The only thing that's different is the mass is a little bit bigger. The mass is 1,280 MeV. Quite a bit bigger than that. It was only 2. That's now, it's like almost 1,000 times bigger right here. And then there was something called the strange. S. There's an S bar right there, the anti-strange. Boy, that'd be bad. What is anti-strange? I don't know, but and then this has the same charge as this, minus 1/3, and the mass of this one is only 96. You know, so the lower the mass, the earlier they found it, because it's harder to find it the bigger the mass is. They found this in the 60s. They found that one in the early 70s, right here. Okay, that's the second group. And then they found the third group in the 80s and 90s. There's something they called, the next group is the top, T. Again, physicists don't like big names, right? They don't want to spell them out. This is T, and there would be a T bar for the anti-top. The mass of this is even going to be bigger. This is 173,100 MeVs. That one they didn't find until 1995, the top. And then it has the same, all these have the same charge, 2/3. And then you have the bottom. And then you have the anti-bottom right there. And this one is 4,180. They don't know why they all have crazy masses, but there's no rhyme or reason to them right there. Okay, so those are the three families. There's only 6 quarks and 6 anti-quarks right here. I should say, you know, these come in colors too. What colors do these come in? Anti-red, anti-green, anti-blue. Yeah. If you know anything about colors, anti-green is actually a magenta right here and so on. Anti-blue is actually yellow, but we'll just call it anti-blue right here. Okay. Now, if you're going to, you can never see a quark all by itself in nature. It's impossible. You can never just find an up quark. They always come together in pieces right here, in composites right there. And why? Because whenever you put your quarks together, they have to be colorless right here. And if you just have one up quark, it's not colorless. It's either a red, a green, or a blue. So how can I get a colorless object out of just red, greens, and blues? Well, I could get one of each right here. So I could have 3 quarks right here. So from here, I could make composite stuff. Composite particles. So I could either make them with 3 quarks, which they give them a name. They call them baryons. Actually, I should say all of these put together are composite particles. Out of these are hadrons. But if you just make them out of 3 quarks, those are called baryons. And if you make them, you can make them also out of 2 quarks. And those are called mesons. Okay, so how can I, first of all, how can I make them out of 3 quarks? Well, if you grab, let's say, 2 ups and a down. So one's a red, one's a green, and one's a blue. Doesn't matter which one, but one is each. So that means this is colorless right here. If you look at the total charge of this one composite particle, it's 2 of these ups. So it's 2 of those would make it 4/3, and 1 of these minus 1/3, that's 1. So this is the charge of +1. This is actually the proton. This is the proton right here. Now, I haven't put down the half-lives because these guys don't decay, but this is the only stable, actually of all the hadrons, it's the only one that's stable right here. This one is stable. And if you look at the mass, we already got the mass. I think we wrote it down before. It was 938 MeV. We did that on some of the problems right there. Okay, well, what if we had 2 downs and an up? 2 downs and an up right here. Now, 2 downs, 2 of these gives you minus 2/3 plus positive 2/3. That's 0. This has 0 charge. This is the neutron. It's the neutron right here. And this one is a little bit heavier. Sorry, what is the mass? Do I give you the mass of the neutron? I think the mass of the neutron, yeah, is slightly heavier. I think it's like 939. This one just a tiny bit more right here. So this thing can decay into this. This can't decay this way, right here. This way, this is not stable right here. It might be stable with other guys, but not by himself. So this is unstable by himself right here. Okay, there's a neutron. Now I could make other particles besides the protons and the neutrons. I could make things called lambdas, and just by grabbing, instead of 2 ups and a down, I could grab 2 charms and a top, or 2 of these and 1 of these, and so on. And so I could make up all of these particles. The reason why we don't see them is because they're very unstable, and everything is heading toward the proton and the neutron right here. And again, when the neutron's with the protons in the nucleus, they're stable. Most of them are stable. Okay. Now, what about over here on this side, right here? How do we get a colorless object with just 2 quarks? Well, if you have something like an up and an anti-down, if this were red and this is anti-red, red and anti-red is colorless right here. So it's going to always be a quark and an anti-quark. And you notice the charge. If I have one of these, remember, if I have an up, let's just say an up, and an anti-down. The up has a charge of 2/3. The down has a charge of minus 1/3, but the anti-down has the opposite charge, so that's 1/3 plus 2/3 is 1. So this has a charge of +1. And the name of this is actually something called a pion. Pion. It's a little plus there. There's a plus charge to it. And we don't see these around. You can create them in particle collisions, but they decay right away. All the pions, none of them are stable right here. There's pions, there's kaons, and they're always a quark and another anti-quark of something else right here. Okay. Now coming back to here, we haven't gone through the leptons right here. The leptons don't hang out in the nucleus. One of them we already know, it's the electron. Electron. E. Okay, we know it has an anti-electron, which we call the positron right here. Same mass, just has the opposite charge. We know the electron is just minus E, the charge of the electron, and we knew the mass of the electron which is 0.5 MeV. And then there's something called the neutrino. Neutrino. They use that symbol for the neutrino, and it's the electron's neutrino. Now, this mass is so small that we're just going to assume it's about 0 right here. So the mass, anytime we see a neutrino, we can assume it's 0. It's not, but it's so close, it's millions of times smaller than this. It has no charge. It does have an anti-particle, you put a little bar over it right there. So that would be the anti-electron's anti-neutrino right here. And we can assume that these, since they have 0 mass, these guys go at the speed of light right here. Okay, and now these all have spins of half too, right here, just all these. Okay, and then over here, these 4 particles right here, considered a family. You can see the parents, the kids, infant pretty much right there. You can make the entire periodic table with this. You can make an entire universe with this. Remember, you can make the protons and neutrons with this, and here's the electrons. They certainly don't feel the strong force, so they don't hang out in the nucleus. They're outside on the outside edge right here. So, okay, so this would be considered the first family, but there must be a family that goes along with each one of these right here. This next one, we did this before. This was our muons. It's a minus charge. And remember, it's just like this. It's just heavier. It has an anti-muon, mu plus, and the charge is just the same as it's still just minus E. The mass we said was like 200 times bigger, so it's like 105 MeV. Okay, and then you also have the neutrino over here. Neutrino. It's the muon's neutrino. Right here. He has his own. Each one of these has their own neutrino. Again, it's going to have the same properties. It has an anti one, it has 0 charge and 0 mass, and almost 0. A little bit heavier, but it's still, we can assume it's 0 right here. So this is still 0, 0, and then we'll assume that this is around 0, pretty much going the speed of light. And then the last one right here for this, so this is the second family. And again, you could make a whole universe here, but they all decay down into here. That's why this is all we see. And then you have the third. To make out the third family, we have the tau. Again, it has the same charge as the electron. The only difference is it's just even heavier than the muon right here. This thing has a mass of about, the mass is 1,776. Remember, this is only 105 MeV. So this is a really fat electron right here. Other than that, it's exactly like it, but it doesn't last very long. And then down here, just like you'd expect, there's a neutrino. And this is the tau's neutrino. And he would have an anti-tau's neutrino, and he'd have 0 mass and 0 charge, and its speed, it's a little bit heavier, but it's still, we can assume that the mass is 0 right there. But it's not exactly 0. Okay, so what do we have here? We've got 2, 4, 6 quarks, and they're anti-quarks. We've got 6 leptons and their anti-leptons. That makes up all the fundamental fermion particles. And then you had these particles that controlled the force. And now once you have these particles, now you can start building up things, and you can make a whole bunch of other things. 3 quark systems, which are like the protons and neutrons and a whole bunch of other things, and the mesons right here. Now, they're still looking for other particles at CERN. They don't think there's any more families. That's it. But one of the things they expect is something called supersymmetry. symmetry. That means for every boson, there's an equal and opposite fermion, and for every fermion, there's an equal and opposite boson. So that this thing really becomes quite symmetric. And what they do is, for every fermion that comes over to here, they just put a little INO on the end. A little INO. INO. So the fermion for this one would be called the photino. This one would be called the wino, W-I-N-O. This would be called the xeno, gluino, higzino, right here. Okay. I don't want to bring that one down there. Over now, likewise, for all the particles that were bosons that now are going to be over on this side, they don't put an INO on the front. They put an S in front of the name. They put an S in front. So these would all be called squirks. Squirks. Sleptons. Selectron. Strandino. I don't know if I could say that right here. Shmuon. And so on. I'm not even going to say them right here, but that's what they would do. But they haven't found them right here. But that's what they're looking for right here. So, but I put down all the ones that I did have right here. So in the book, when they say some sort of pion is running and decays or something, we'll know that it was probably some pion right here, and these aren't they don't live very long. They'll decay into other particles. They're going to decay probably into muons and other things right here. And again, you can't just decay into an up right here. And so there's the fundamentals, just a quick overview on the fundamental particles. Okay.